Hello, and welcome to our machine learning final project. My name is Noah Kohls, and I've been working with Sebastian, Hogan, Matt, and Tommy on character recognition for automated equation generation. Our motivation for this project is that we want to combine the speed and simplicity of developing handwritten equations with the formality and legibility of typed equations. To do this, our problem definition was to develop a machine learning algorithm that will take an image with equation in it and convert it to an equation-based text, as you can see in the figure at the bottom. The machine learning algorithm is separated into three main stages. In the first stage, the equation image is segmented into individual characters by binarizing the image and performing DB scan to obtain clusters for each individual character. In the next stage, we attempted to separate the individual characters into clusters based on the case of each letter. Our training dataset contained over 375,000 labeled images of individual characters, including both numbers and letters. But one issue we observed was that the dataset for the letters were labeled too generally, and we could not distinguish between capital and lowercase letters. One approach we took to separate the data was to implement feature engineering. This way we could reduce the dimensionality of the image and find features for each image that were unique to each case. We looked at intensity, horizontal symmetry, vertical symmetry, area to perimeter ratio, and the height to width ratio. However, as you can see from the figure to the right, these features didn't provide enough information to make distinct clusters, and we had low accuracy when predicting the label for each cluster. Next, we tried using principal component analysis to separate the clusters. This would again reduce the dimensionality of the image from over 2,000 features to just the top few features that represent the highest variance. As you can see from the image on the bottom, PCA does a great job of separating the data visually. Once the data is represented with its principal components, we attempted to find clusters using both k-means and Gaussian mixture models. As you can see, GMM did a better job of more accurately clustering the data because it is able to find the correlation between the two principal components. The final stage in our algorithm is to implement traditional supervised learning techniques to label each character. First, we split the data into 70% training and 30% testing data. We attempted to use decision trees, support vector machines, and even naive Bayes to properly label the images. And while these techniques did a pretty good job of labeling the dataset, they did not generalize on our personally handwritten images and had accuracies of less than 10% when predicting the equations. Because of the low accuracies on our handwritten equations, we implemented a convolution neural network with a modified version of ResNet 18 that could be used for grayscale images. The architecture is built from 69 layers and optimizes over 11 million parameters. We needed to make sure that the training data was more generalizable for handwritten equations, so I modified the images going into the network by eroding, padding, and resizing the image. The final model was trained with an atom optimizer and a learning rate that decreased over the set of epochs. We also attempted to build our own more simplified CNN that had only 16 layers and required 9 million fewer parameters than the ResNet model. The images for this network were also modified to be more generalizable for handwritten equations. And similarly, we used stochastic gradient descent optimizer and 5 epochs to train on this network. The ResNet model ultimately had better accuracy, so we stuck with this model and trained on the entire data set. Here we have two example ROC curves for a comma and the letter O. For each symbol, we calculated the average area under the curve of 0.99, which suggests that the model is highly accurate for the dataset that we provided it. Since the model is able to properly label the characters, we started testing it using personally handwritten equations. Overall, the model does a good job of identifying each of the characters in the equation. However, there are some instances where the model does mislabel a character. You can see in the second equation, it mistook the equal sign as a summation sign, and in the third equation, it mistakes an O as 0. Overall, the results are promising, and the model was able to consistently output the expected equation with over 80% accuracy. Finally, we needed to reconstruct the equation to a format that we could provide to an equation editor. In this case, we chose LaTeX. We developed a Python script that takes in the image labels and the location of each character and outputs an equation that can be used directly in LaTeX. The script is generalizable for exponents and sequences of letters. The equations below are from our best results, which predict the handwritten equation with 100% accuracy. In conclusion, we successfully demonstrated handwriting recognition on a simple single-line equations. This figure shows an overview of our entire model. We used unsupervised learning for character clustering, which is then fed into supervised learning models. We ultimately had the most success with the CNN. In the future, we can improve this model by implementing some time dependency to improve sequence identification, which could help identify things like sine, cosine, and log. And we could also train on entire equations rather than individual characters, which might help improve character labeling for things like O, 0, and capital O. Finally, we only used single-line equations, but this implementation could be expanded for multi-line or more complex equations. Thank you for a great semester, and thank you to my team for a great project.